Hello and welcome back to PC Retro Programmer. In the previous video we looked at the main idea behind the Cordic algorithm for rotating points about the origin. We saw that if you have a point written in vector form like this, all you have to do to rotate it is to multiply by this rotation matrix, and this will rotate the point counterclockwise by an angle theta. And then we use the main idea behind the Cordic algorithm to reduce the matrix to a much simpler form like this. And we said that we could actually choose a very nice value for tan of theta. And I think I said I'd use either 1 on 8 or 1 on 16 as an example. And this matrix is then very simple to use, so long as we also multiply by this constant cos theta that we pulled out the front here. Before I do any coding, let me compute the k value that we're going to hard code into our program for the Cordic implementation. I've decided to use tan theta equals 1 on 8 for my code, and so let's put that in. That's the value 0.125, and the value that we want for k is cos of theta, and this is tan of theta. So how do we get from one to the other? Well, somehow we have to reverse the tan function to get back to theta, and then we have to apply the cosine function to get our value k. So to reverse the tan function, there's a function called tan to the minus 1 on this calculator. It's a little bit misleadingly named. It doesn't mean 1 on tan, it's really the inverse of the tan function. And so what I need to do is apply that, and that'll give me the angle theta, and then I can just apply the cosine function. So if I left it in the degrees mode here, you can see that at the top of the display, it would give me the angle theta in degrees. But I'm actually going to switch it to radians. It really doesn't matter for this whole computation because neither the input nor the output are actually angles. So long as we're consistent throughout the computation, it doesn't really matter for the final result. But for this intermediate part where I'm going to compute theta, the angle theta, I want to do it in radians because I want to show you just how close theta and tan theta are to one another. So this is tan theta, 0.125, and if I invert the tan function and go back to theta, it's 0.124. So you see when the angles are very small, theta and tan theta are very close together if you're in the radians mode. So now I can just apply the cosine function to this, and this will be my value k. But one little problem with this is it's just a decimal value, and what's more, it's a fractional decimal value. So how do I compute this to something I can use on a binary computer? Well, what I can do is multiply this by 256, and that will actually give me the first byte after the decimal point. Well, actually the binary point, I suppose we need to call it. So the first byte needs to contain the value 254. Now, obviously that's the decimal value 254, but we'll just convert it into hexadecimal. So that's the first byte, so let's subtract that off, assume that we've dealt with that. And how do we get the next byte? Well, same procedure, 256 times gives us 5, and so that's the second byte after the binary point. So let's subtract the 5 off, and that's what we're left with. So now we need to compute the third byte after the binary point, so let's multiply by 256 again, and we get the value 236. So once again, once we convert that 236 into hexadecimal, that will be the third hexadecimal byte after the, well, hexadecimal point or binary point, whatever you want to call it. So that is a 3-byte approximation to our k value. And if I took that 236 off, there's something left there, but this is just a very, very small remainder from the 4th byte onwards, which we'll just throw away. We're just going to do a 3-byte approximation. So now we have our k value, we can actually code up our Cordic algorithm. Well, it's time to have a look at the code that I've written for this, and I've called this Cordic1.asm. It's a hard piece of code because it has to do approximations. After all, that k value is cos of theta, which is certainly fractional, it's not an integer. So there's two ways that I could have handled this. I could have used floating point arithmetic and even a floating point coprocessor, but I actually think that would be slower than what I'm going to do, which is to use fixed point arithmetic. So fixed point is where you have a fixed number of bits before and after the binary point. And in this case, I'm going to use 8 bits before the binary point and 16 bits after the binary point. So 24 bits in total, or 3 bytes. And I can actually represent these just using 3 bytes in memory or in registers, and just keep in my mind where the binary point is. So of course the processor itself has no idea about fixed point arithmetic. We have to really think for it in that case. Now the choice of 8 bits before and 16 bits after the binary point is pretty common for CGA graphics. It allows you in that 8 bits before the binary point to represent signed integer values from -128 to +127. And in my case, I'm just going to be animating a line. It's going to be of length 100, and I'm going to be rotating it about one of its endpoints. And so I really don't need integer values bigger than 100 in the positive or negative direction. So they're going to fit just fine in that 8 bits before the binary point, including the sign. And unfortunately we can't just use 8 bits after the binary point because we don't get sufficiently good approximations. I'm going to be applying Cordic over and over again to rotate this thing, and each time we do that there's a little bit of error accumulates. And so I really need to have a full 16 bits after the binary point. But this means that I need 1.5 registers, 16-bit registers, to store the values, and it just doesn't seem to be possible to do the entire computation that way, so I'm going to have to allocate some space in memory for some values. Now I could have used local variables for this on the stack, but in the end I just decided to put a couple of values into the data segment, so global variables as they're called. Now there's going to be 2 values here, the xi and yi. These are the actual coordinates of the vector that we're going to be rotating. And these have to be stored as 24-bit values. I can't just use integers here, because once you apply Cordic even to integer values, you get something that's not an integer. And if I just kept rounding back to an integer again, I'd just be accumulating massive amounts of error. So I really have to keep these in the 24-bit fixed point. So there are 2 values, xi and yi, and the first 16 bits of each of those are here, x high and y high. So this includes the 8 bits before and 8 bits immediately after the binary point in each case. And then of course there's 1 byte left in each case, and I store those together in the same word which I've called low. I think the high part of this is the final byte of x, for example. So there are 3 parts to this algorithm. There's the Cordic multiplication, which is multiplication by k, and this turns out to be the hardest part of this computation. Then there's the Cordic algorithm to multiply by that matrix and then to call this Cordic mul, and this is not a particularly complicated piece of code. It's quite nice. And then the final part is the animation. This will draw the line. Obviously it then has to compute the transform of that using Cordic, blank the original line and redraw the line in the new position, and it'll do that over and over again. So let's start off with the Cordic mul procedure. Now this Cordic multiplication by k function here is actually going to be a little bit different than normal. So normally when you pass arguments to a function, you pass them on the stack. But this particular function is only ever called from the main Cordic implementation, which is further down. It'll get called twice, but the values are already in registers at that point. So why bother to put them into the stack, then pull them back off the stack once we get inside this function, and then continue on? Why not just leave them in registers right from the start and just skip the stack entirely? Now we can do this because this Cordic mul routine is not designed to be called by anyone else, so we don't have to worry about anyone else's calling conventions. We can pass the arguments however we like. So we're going to pass them in the AX and BH registers. Now that's 24 bits, and obviously we need to do two Cordic moles, but this function will just be called twice. So this particular routine is designed just to do one of the multiplications by k. So it'll take this input value and multiply by this k value, and this is the cosine of arctan of 1/8 that we worked out on our calculator. So we got a 3-byte approximation to this, and the idea is that we're going to need to multiply the 3-byte input by that 3-byte approximation. And normally, if you multiply 3 bytes by 3 bytes, you get 6 bytes. But we're only interested in maintaining a 3-byte approximation for the answer. So what we're going to do is throw away the trailing 3 bytes. We'll just take the top 3 bytes of the product. And the result is going to also be returned in the same registers that the input came in, namely AX and BH. So the k value that we worked out on the calculator, what we did is multiply it by 256 3 times. And so if we'd actually just written that out as a single large integer, we would have got this value here. On the calculator, of course, we worked out each byte of this value individually. So the problem with this value is that there are a hell of a lot of ones in its binary representation. And normally when you do multiplication in binary, what you do is you take the input and you shift it left lots of times, and you just move along through the bits of the multiplicand, and every time you get a 1 in the multiplicand, you add the shifted value so far to the result. But if there's lots of 1s in this multiplicand, that's going to be a very, very expensive operation. So there's actually a little trick that we can use to speed this up, and that is to not just add shifted copies of the input, but to also allow ourselves to subtract shifted copies of the input. And so that means writing this value, this multiplicand, not just as a binary value with just ones added in various columns, but to also allow subtractions in the representation. So what this means is that instead of just adding shifted values, for example here, we would end up subtracting shifted values. So this is literally telling us that we're going to shift the input right by 8 bits to get the 256 squared on 256 cubed. Remember, we're actually multiplying by this value divided by 256 cubed. And then shift it left by 1 bit to get the multiplication by 2. And then we're going to subtract that shifted value from the result. So that's just a little trick that we can use in binary to speed up binary multiplication. Well, where on earth do we start in order to handle this product that we've got to do? So this is the value that we've got to multiply our input AX BH by, and we want the result to also be in AX BH. And it's actually not really this value, but this value divided by 256 cubed that we're multiplying by. And so this first term really corresponds to multiplication of our input by 256 cubed divided by 256 cubed. In other words, multiply our input by 1. And since our output's going to be in the same place as our input, this is really trivial. We don't have to do anything to handle that. But these other terms now say that we have to add or subtract various shifts of our input from that output. So what I'm going to have to do is make a copy of my input in order to shift it about. So I decided to use the DL and CX registers for that. There's 3 bytes here, and so we'll make a copy of our input into this, ready to start shifting it. But whenever we do shifts here, it looks like we're at least shifting by a byte here. We've got 256 squared divided by 256 cubed. And when we multiply by that, it's the same thing as shifting right by 8 bits. So basically, what I'm going to do to shift my input right by 8 bits is I'm going to make our 3-byte input into a 4-byte value and just blank out the top byte. So in other words, I'm going to copy the input into DLCX and then just blank out the high byte of DX. So it'll just be dh equal to 0. And that'll give me my input shifted right by a byte, or effectively so. But this isn't quite correct, and the reason is because this input could have been negative. After all, we're transforming coordinates here, and coordinates could be positive or negative. And shifting a negative value right by 8 bits will actually require sign extension. So basically you need all ones in that top byte that's left behind if the input's negative. So this is something that the arithmetic shift instruction SAR normally handles. If I shift right by a bit with SAR, it automatically maintains the sign. So if this input was negative, it puts a 1 in the bit that's left behind after the shift. And so if I did 8 of those, I'd end up with all ones in the top byte, which is going to be my DH register. But of course, doing a shift right by 8 bits using 8 SAR instructions is pretty inefficient. It'd be much easier just to copy all the bytes into DLCX and then handle DH separately. Basically, all I need to do is just set DH to all ones if the input was negative. So at the end of the day, what I end up with is a sign extended copy of AXBH into DXCX. Now it turns out there's an instruction that helps us out with this, and it's actually for sign extension. It's this CWD instruction here. What it does is sign extend AX into DX, and that's actually going to be really convenient here because our input came in AX, and we're actually wanting our sign extension into DH. This is actually going to sign extend into DX, not just DH, so it'll actually be all ones in DX if the input was negative, but that's fine because we're going to overwrite DL anyway when we make a copy of the 3-byte input. So that's what these next lines do. They just copy AXBH, our input, into DLCX, the remaining 3 bytes of DXCX. So now we have a sign extended copy of our input into 4 bytes. So now we're ready to start doing our shifts, and the first one that's called for is a shift left by 1 bit in order to handle this multiplication by 2 here. Now it turns out we'll be able to use that value again here. So what that means is that we take the input value, which we've already worked out for here, and shift it right by another byte for this term here. But of course, we've just learned that shifting right by a byte means you have to worry about the sign. So we have to think about what will be the effect of adding this shift on if that value was negative. Well, of course, we'd again leave a byte of all ones behind after the shift, and so the effect would be that we would actually be adding FF to the top byte of the output, in other words, to the AH register. So adding FF is the same as subtracting 1. So basically, if the input is negative, we have to subtract 1 from the AH register to handle the sign extension problem here. So let's see how that all works out. Here's our multiplication by 2, our left shift by 1 bit. It's just these 2 instructions. And fortunately, if the input is negative, the carry flag would automatically be set after this shift. It just shifts out the top bit of DX and puts it in the carry. So we can actually use that to deal with our sign extension problem. Remember I said we just have to subtract 1 from the AH register in that case, and that's precisely what this sub with borrow will do if the carry is set. So sign extension problem solved. So now we're actually ready to use our 2 times vals. Basically, we just subtracted off here and then added on again, shifted right by an additional byte here. Now, unfortunately, you can't add an 8-bit register to a 16-bit register, so in order to add DH to AX, we actually have to do 2 instructions here, as add here and then an add with carry to propagate any carries through to the rest of AH. but at least this is not very expensive. So we've now taken care of our 2 times values. So the next ones to deal with are the 4 times values, and we have it here, albeit shifted right by 2 bytes this time, and here shifted right by 3 bytes. So we're actually going to have sign extension issues for both of these. But again, let's think about what that means. Here, just as we had with the 2, we're going to have to add an FF to the AH register, and this one here would end up having us subtract FFFF from the AX register. But if you combine those two things, add FF to AH and subtract FFFF from AX, the combined effect is to subtract FF from AL. So let's see how we handle that in practice. Now I actually couldn't find a really nice way to do this in assembly language, so first of all we do our shift left by an additional bit, so now we have 4 times our input. That's handled here, and again the carry will be set if that input was negative. So if there's no carry, there's nothing to do, there's no sign extension to worry about, so we just jump over this. But if there is a sign extension problem, as I said, we have to subtract FF from the AL register. And of course we need to propagate that through to AH. Fortunately, in assembly language you can actually subtract an 8-bit immediate value from a 16-bit register, so that can be done in one instruction. But anyway, that handles our sign extension problem for those 2 different parts of the sum. So now we can actually do those 2 parts of the sum. There's the addition of 4 times val, obviously shifted right by 1 byte, and propagate the carry through again just as we had above. And then we have to subtract 4 times the val, now shifted by 2 bytes, and that's what this looks like here. And again, there could be a carry which we'd need to propagate through to the remainder of the output. So that takes care of our 4 times vals. So the only remaining part of our product is the 16 times part, and this is the term here. Now this is going to have a sign extension problem as well, and in this case we're going to have to subtract FFFF from the AX register. In other words, we'd have to add 1 to the AX register if the input was negative. So let's see how that all works out. So down here, the first thing we have to do is multiply by 4 again, so that we now have a product by 16. So it's just another 2 left shifts by 1 bit. And you'll notice that I don't actually shift the CX register here, and the reason for that is I'm actually not going to use it below, and you'll see why in a moment. We could have put that in here, it just would have been wasted effort. So here is where we deal with our sign extension issue. Once again, this shift here would leave the carry set if the input had been negative, and so we basically end up just adding the carry to the AX register here to deal with that sign extension issue. So then we're ready to actually deal with our 16 times val, and all that needed to happen was to subtract it, shifted right by 2 bytes of course, and that means that it only affects the very last byte of the output. Now this is why we didn't have to do anything with the CX register. You can see I only used DH here, so I didn't need to shift CX at all because I don't actually use it when I do the subtraction of the 16 times val. And as usual, just need to propagate any carries through for the rest of the output. But that is our Cordic mul routine. So now we basically have an entire Cordic multiplication implemented. And you can see that I didn't actually bother saving or restoring any registers in this routine, which is really nice. And the reason for that is that the only registers we actually messed up in this routine are CX and DX that we put our copy of the input in. And it turns out that the actual Cordic routine, which is below, doesn't actually need the CX or DX registers after we call Cordic mul. So that worked out really nicely. It means that this will be very, very efficient to call. So that's the complete implementation of the Cordic multiplication, which, as I mentioned before, gets called twice by the Cordic algorithm.